Hello, this is Psych, and welcome back to my channel. Today, I'm going to address how we can actually use SPSS in order to investigate reliability. All right, so I've created a data set here that is basically going to allow us to look at the three different situations that I've mentioned. So at first, we're going to look at alpha. Then we will look at alternate forms reliability, followed by test-retest. So in this situation, I've got, let's say, 5 items on a questionnaire of some sort. Let's pretend that this is some kind of attitudes toward math questionnaire where students are asked to rate the extent to which they agree or disagree with statements on a 1 to 5 scale. And since all of these items are designed or written to measure the same thing, with alpha, what we're really interested in is basically if students tend to agree with the first item, they should also have a tendency to agree with the other items. So we're going to look at the consistency of scores between these items. So to look at alpha, let's go to Analyze, Scale, and Reliability Analysis. I am going to put in all 5 items over here. And then I always think that it's a good practice to just review the options that you have here. So let's just look at the different options that we have. Why not get some descriptives for the items, scale, correlations, summary, means, correlations and variances, and that's all that we would really need in this situation. Let's hit continue. And you can see here that there's different options. We're going to select alpha, which is the default. And if you want to use syntax or record this, you can just paste this into your syntax, but we're going to keep it simple. Just click OK. Let's take a look at our output. Okay, so I've got 20 people, and you can see that I've got 2 different values here for alpha. We are interested in this first value for alpha. We also are provided with the second alpha. However, we would only use this second value in situations where our items are what we would call, I don't want to do this, standardized, and we would standardize. So it's kind of like looking at alpha with z-scores. We would only probably be interested in using the second value in situations in which you might have items that are on a different scale, though they're all designed to measure the same thing. So, for example, you may have one item that's on a 1, a yes or no, another item that's on a 1 to 5 scale, maybe another item on a 1 to 7 scale, and so forth. In cases like that, you might be interested in this other value, but most of the time you're going to use this first value. You can see that our alpha value is 0.335, which, to be perfectly candid, is quite horrible. So why might this be the case? Let's just start taking a look at some of these items. So we've got descriptive statistics here, and all of the means are like 2 or so. We have another mean here that's a bit higher than the others. All the standard deviations are fairly close to being the same. But what do we notice about the inner item correlation matrix? If we look here, we are going to see that we have a lot of negative values. in particular, more specifically with Math 5R. So Math 5R has a negative correlation with Math, the first item, second item, and so forth. And if you look at this box here with our summary statistics, you can see that the average inter-item correlation is 0.14. Alpha is going to, the bigger that this number becomes, basically the bigger our alpha is going to become, holding everything else equal. This is pretty low, which is one of the reasons that we're seeing this low value. And that is deriving from the fact that we've got negative numbers here in our correlation matrix. This item total statistics, this is where we would get information about item discrimination. I've not really talked about discrimination in some of my other videos, but I think I could do a separate series on item analysis. But with respect to discrimination, we would look at this corrected item to total correlation. And basically, that's the correlation between the item and the total score after we have removed the item from the calculation of the total score. And discrimination as a concept in measurement theory is basically this idea that we want our items to be able to differentiate people at different levels of, let's say, agreement or different levels of a construct. Sorry. And so basically, people who tend to agree with this item would also have a tendency to, let's say, have higher overall scores. We want that discrimination value to usually be at least around 0.4 or greater. We have negative discrimination with our 5R item. That's another issue, basically. Our alpha, if item deleted, is going to look a bit kind of crazy because of the situation that we're in. But basically, it's saying, hey, if we get rid of this Math 5R item, our alpha is going to get much better. So we don't want to delete that item immediately. The fact that we've got this negative correlation here is simply due to the fact that this item needs to be reverse scored prior to my calculations. So I'm going to go back to the data set. What I mean by the fact that this needs to be reverse scored is basically this item would, it needs to be scored in the opposite direction. So agreement with one would actually mean disagreement with the other. So for example, one item might be, I am afraid of math. And the other item might be, I love math. These are items that are in the opposite direction. And when we're, prior to conducting our analysis, we want to make sure that all of the items are scored in the same direction. So this item here needs to be reverse scored. So let's go ahead and do that. There are various ways that we can reverse score an item, and I'm just going to show you one way to do it. So let's go to transform and recode into a different variable. I'm going to put my Math 5 item over here. You're going to see this question mark show up. Basically, we need to give this new variable a name. So I'm going to call it Math 5 recoded. You can name it whatever you want to. Just be sure not to include any spaces because for some reason SPSS does not like spaces. So after that, we will click change. And then I need to click on this old and new values. And this is where I'm going to tell SPSS, these are my original scores. What do I want the new scores to look like? So now we've got a new box that pops up. On the left-hand side, we can see my old values. On the right-hand side, I'm going to give it a new value. If we want to reverse score this, then let's say anything that was a 1 would become a 5. And I'm going to add that. Anything that was a 2 would become a 4. Anything that was a 3 would stay a 3. Anything that was a 4 would become a 2. And anything that was a 5 would then become a 1. After we are done with that, we would hit continue and then OK. Now you're going to notice that in my output, nothing has changed. The only thing that has changed would be this information down here. And this is actually syntax. If you want to save that and save it for later, put it into a syntax file, you can do that. But it looks like nothing really has happened. But you'll notice over here, I've got this math5 recoded variable. Just going to double click that and change it to being a scale. You can put scale or ordinal. For our purposes, it's not really going to matter. There are cases or situations in which it does matter, but for what we're doing, it doesn't really matter if it's a scale or ordinal. Okay, so let's go back to my other view. So you can see that basically the only thing that happened is it's created this new variable here. So let's redo our analysis. I'm going to go to scale reliability analysis. I'm going to take out the original variable and then include my new variable. All of my options should be the same. So let's just click OK. And now I've got my new output here. You can see that alpha has now become 0.918. It's much improved. If we look at my inter-item correlation matrix, all of these are also now making sense. I like the summary table here because we can see that that correlation matrix has a range of 0.542 to a maximum of 0.789 with an average value of 0.70. And that's basically why we see this huge improvement to coefficient alpha. Let's take another look at the item total statistics. I'm looking at this corrected item total correlation column. That is, like I said, we call that discrimination. We want those values to at least be 0.4 or so, and all of these are super high. The alpha if item deleted. In order to read this table, I need to know what my original alpha was. So for example, this alpha here was 0.918. So let's keep that in mind. I'm going to blow this, or at least get this where I can kind of like highlight it and so forth. So what would happen if we delete item 1? Well, my alpha would drop from 0.918 to 0.888. If I get rid of item 2, my alpha is going to decrease to 0.90. So in other words, if we remove the item, that item, we're going to have less reliable scores. That's basically saying that the item's good. Do we have any items that are not good? No. So all of these items would look good. So that's a very brief overview of internal consistency. So now that we've done that, let's take a look at alternate forms reliability. So we're not going to worry about the other variables. Let's just pretend that in this very basic situation, I've got 20 students here that are my rows, and I've got Form 1 and Form 2. So I have created 2 different math exams, and I want to examine alternate forms reliability. In order to do that, all that we have to do is look at the correlation between Form 1 and Form 2. So I'm going to go to Analyze, correlate, bivariate, and then I will put form 1 over here and also form 2. Like I said, it never hurts to look at the different options that you have. This box pops up here. Why not get the means and standard deviations? Style. I don't ever mess with this, and bootstrapping. That's kind of like a mini simulation type of procedure. We're going to leave that alone. And that's really all that we have to do in this case. So let's click OK. And then I see my output here. Form 1 had a mean of 70, standard deviation of 17. Form 2 had a mean of 72, and a standard deviation of 14. If I look at the correlation between the two forms, which is my alternate forms reliability, we want that correlation to be around 0.9 or more. In this case, we have a correlation of 0.937. So what this is indicating is that students who are doing well on one form, let's say relative to others, also has a tendency to do very well on the other form. So in this case, with a correlation of this magnitude, we could probably, let's say we could substitute one form for the other and not really be worried about the conclusions that we would reach about relative student differences. So in this case, everything looks good. All right, so for the final situation, let's take a look at test-retest reliability. Let's go back here to my data set. Now we're just going to do the same thing, except let's pretend that I have 20 students who were tested at time 1. These students were then tested at a different point in time. So to do this, once again, we just need to look at the correlations. So I'm going to go to Analyze, Correlate, and Bivariate. Let's remove what we had before with respect to the test forms. And now I will put in time 1 and time 2. Let's look at the results that we get. Here we can see that at time 1, we had a mean of 66. Time 2, mean of 69, so went up a bit. Standard deviation of 19 and 14. The test-retest correlation is 0.659, which is a bit lower than what we would want, in particular when we are going to take scores at one point in time and use them to make decisions at a different point in time. So I've purposefully set this up to be a bit strange. So let's go ahead and look at a graph. I might go to Graphs and Chart Builder. And let's go to a scatter. Let's make a scatter plot. I'm going to put the scatter plot over here. You can see that this fills up. And let's put time 1 on the x-axis, time 2 on the y. I think that should be sufficient for what we're doing. Let's click OK and see what we get. Now you can see that at like I said, the x-axis we have time 1, y-axis we have time 2. These are on a different scale. You could put them on the same scale if you wanted to, but just for our purposes, you can see it's not really necessary. If you were going to publish it or something like that, it probably would be necessary. But you can see that we've got a nice, if you were to try to draw a straight line through here, we do have a nice line that we could draw through here. Reliability, since reliability is really based on correlations, anything that affects a correlation can also impact reliability. So what do we have over here with this student, this dot? Well, they had a very low score on time 1, and they had a pretty good score at time 2. So if I was going to use scores at time 1 and make decisions about what to do with their math, let's say at time 2, this student really doesn't fit um, our expectations. So perhaps maybe, let's say this student, maybe they've learned some math or something in between our two testing occasions. So let's see what would happen if to our reliability, our test-retest correlation, if we remove this student, it should go up quite a bit. So know that this is student 15 here. They had a really low score at time 1, high score at time 2. I wouldn't suggest that you actually delete. I'm just doing this to try to keep the video kind of reasonable. Let's just cut this person, or delete this person. Let's go back to the analysis. Oops, I went to the wrong thing. Let's go back to analyze, correlate and bivariate, and just redo it. You can see now our reliability estimate's much better, so we have an outlier in the first case. So that's a brief overview of alpha, alternate forms, and test-retest.